Okay, today we will move on and we try to discuss the left part of chapter 10, which involves the excess property calculation. And we will also start the discussion of mixing and some partial property calculation. Because moving forward, the next chapter will be chapter 11 about the mixing, chapter 12 and chapter 13 about the vapor liquid equilibrium. Which is basically a revisit of the chemical potential and fugacity discussion. And then over there, for instance, in chapter 13, we were mainly talking about the liquid phase. We have received enough discussions on the vapor, especially for their fugacity calculations, and we need to see if we try to focus on liquid, what kind of equation, what kind of tools or theory we will have in order to directly deal with liquid phase. Okay, so this is the three chapter and the materials moving forward. We will have another reading assignment today out for the chapter 11 and another homework set out for the chapter 11 as well. So let's try to have a really quick review on the materials we discussed. It's been almost a week since our last discussion. So we were talking about chemical potential, and we tried to derive a bunch of equations to deal with the mixtures. Here for mixtures, we are able to deal with one component, multiple phases, or in the general case, multiple phases, multiple components. So no matter how, we always start with the definition of chemical potential. And the first equation is actually a very useful one, where you are going to have the chemical potential connected with the partial molar Gibbs energy. And then the second very useful equation is now we try to look at, and this is a repeating pattern. Once we derive some new quantity, we try to again express that new quantity as chemical potential, fugacity. Now we try to also express the two new functions as the equation as a function of temperature, pressure, and composition, right? So this is why we received the second equation, which is a partial derivative of chemical potential with respect to pressure, would be the partial molar volume. Okay, and then using that second equation, we started the discussion of ideal gas. We use PV is RT. Then we can simplify, and we receive the equation over here. Okay, so PI is the partial pressure. PI naught is the partial pressure at standard state. This is to remind us this is standard, where T is 1 bar. Okay.
Okay.
And then after those understandings on the ideal gas, we moved on, and Lewis defined the fugacity for any component. So this is the fugacity definition for any component. Nothing special. We just compare the ideal gas equation, and we write down this d chemical potential d mu I is RT d log Fi. And at the ideal gas condition, the fugacity is going to come back, and we can replace that by the partial pressure. Along that same direction, we define a few coefficients. So the fugacity coefficient try to compare the deviation from the ideal gas. We have the activity coefficient, try to look at the deviation from standard state, and then we try to link the liquid phase together. So there we have this activity coefficient. And we are going to have another chapter, which is chapter 13, to specifically looking at those activity coefficient and how we can come up with other equations. Okay, so after those discussion of new quantities, then we jump into the calculations, right? So the most general way is to calculate from the TPX or TVX, whether you have the experimental measurement or you try to move from the equation of state and then solve some correlations and eventually calculate the fugacity coefficient. So there, now we know that we have this fugacity coefficient defined as Fi over Pi. Then the calculation of fugacity is more or less the same as the fugacity coefficient calculation. So that is the method we adopted in the TVX or TPX, those two equations. Okay. And then we also summarize that when we have the gases, we have quite a few cases where we can easily get started. When we have the liquid, then we try to look at the corresponding vapor phase, or we try to look at the correction moving from the low pressure, especially within the saturation pressure, to higher pressure, how we account for the pressure increase. And then for the solid, we did not discuss anything, but we have two understandings. One is generally the solid fugacity should be very small, because the effective partial pressure of the solid material should be very small if molecules are able to escape the solid crystal structure, right? The second understanding is we should have some corresponding liquid phase or vapor phase, and if that is the case, then we use the other liquid or vapor to calculate the fugacity of solid. And then over there, we also have one special case called low solubility, because that's happening in many applications. Water solubility in oil, or the gas phase solubility in liquid or solid. So sometimes those solubilities are very small. So there we have the Henry's law to take care of those calculations. So those would be the previous discussions, and will be in the coming exam, in the exam 3 of next Thursday. So now moving forward, we want to discuss the calculation of excess property. So that is a new quantity we introduced today. So when you look at this excess property definition, I hope this looks very familiar to you, which is E stands for excess, and ME is defined as the property of M at this real condition versus the property of M at ideal liquid. So here we have two notes to add. Number one is, well, this excess property is mainly talking about liquid, okay? And if you recall, we actually have one equation specially designed for gas. And I hope you recall this is the residue property, right? So that is for the gas. Over there, we are interested in M. M very likely would be the following properties. We have four energy equations: internal energy, enthalpy, Helmholtz, Gibbs, and also the volume is always of interest to us, and the entropy is also of interest to us. So very likely when we talk about the thermal property calculations, then we are talking about one of those six properties. So this is the second note. The third note is what do we mean by ideal liquid? Okay, ideal liquid is the property of N I. Let's say it's in a mixture, right? So let's have a head, and we have had two heads so far. One is this head, the other is this head, right? So the first head is to simply remind us this is out of mixture. The second head is a partial head, meaning this is a partial molar property. So when we think about the ideal liquid, then if you somehow recall the Raoult's law, which is the the property of the liquid component in the mixture is proportional to the molar fraction times mi of the pure, right? So that is the equation for the ideal liquid. And the assumption there is I have A, B, C, D. So the AA interaction is very similar to the BB interaction to the AB interaction. So by adding other liquid components, they are not going to mess up my interaction with my fellow molecules. So that is the understanding of the ideal liquid. So here, by the residue property, the excess property, we try to understand whether those intermolecular interactions will make a change in the liquid in the mixture phase. Okay, so that's the definition of excess property. So we then jump into this equation, and we will have a better understanding after a few slides. So here we try to say, well, this is my excess property definition. So we try to manipulate. We try to add this term. Okay. And then, of course, we are going to add that term again in order to keep the balance. And now, if you look at this first term, so here we have the property n, say this is the volume. So capital N is the property of the mixture. This Mi is the pure component property. Then we can see that in the first parenthesis, this is the actual mixing property change. Okay, so when we have water, when we have ethanol, and we have the property of water and ethanol in their pure phase, when we mix the water and ethanol into one liquid phase, then we will have some volume change according to our life experience. So that is a change to mixing. Okay. Then the second is also the change, but this is a change due to mixing for the ideal liquid. So the interesting part is the next equation. If we try to use this mixing property delta M, you can understand this by the volume change due to mixing liquid and ethanol. Then we can see that if I use the excess property definition, this mixing property of excess would be this delta N and delta M ID. And you can see that from the previous equation, this is exactly the same as ME. Okay. So it's a little bit awkward in this equation, but the indication is very useful. That means the excess property is connected with the mixing process. So this is excess property of liquid mixtures. And from this equation, we actually understand that that is connected, or it's expressed by the mixing process. And that is indeed something we have not touched, right? We were talking about this diagram. We say, oh, this is alpha phase, this is the beta phase, and we try to understand this is at equilibrium, right? And we say, how I'm going to have T, P, I'm going to have the chemical potential or fugacity for any component, so on. But the question is, well, we don't have mixture automatically for us, available for us. We have to put something together in order to form the mixture, right? So if I have the component, I have the component 1, I have the component 2, I have the component 3, so on, and then they are going to form this mixture phase. So now if I'm going to add those pure components together, is there any change in terms of volume? Is there any change in terms of enthalpy, entropy, and all the other energy equations? So this is why the mixing process is also very important. We need to understand by mixing those pure components, what would be the change? So this is why we are
That
going
has
to.
nothing to do with.
I'm sorry.
So it's nothing to do with reactions. It's just when you mix two substances, you will have changes in, I assume, temperature, pressure, and chemical potential. And
No, I did
different.
not. I did not say that. By mixing, you could have only phase splitting. Say,
Okay.
say I'm going to have liquid water, liquid ethanol. You add them all together at room temperature 1 atm. That is purely two liquids forming one liquid mixture, right? However,
Okay.
However, if you have that mixing process at extremely high temperature, then they may react. Say if you have hydrogen gas mixing with oxygen gas at some specific temperature, then the two gas pure components may react and may produce water for you. So
Okay.
the mixing is a general process, and it could be quite complicated. So this is why we need to understand. Now I started with the pure components. I try to add the pure components together, and I want to understand. One is how they are going to mix with each other. The second is, well, at equilibrium, what would be the understanding over there? So we hopefully we have addressed the equilibrium uh, in a very general way. Now we try to
Okay.
understand the previous step of the mixing. And after that, we are going to have two special discussions, which will be the last part of the thermal class, meaning one special case is purely for liquid vapor equilibrium, no reaction, simply phase change when we have the mixing. The second special discussion is we try to look at the reactions by putting components together along the mixing process. So we are getting closer to the more interesting stuff, but we need to take care one by one, all right? So this is the reason of having those manipulations and try to understand that the excess property is going to be helpful for the mixing process. So moving forward, I have this slide which I've explained that keep it in comparison when we are dealing with liquid phase. Then I hope you think of the excess property. We try to understand the difference. We are always interested in the reference and try to understand the deviation from one to the other. So this is why we have the real liquid, we have the ideal liquid, we have the real gas, we have the ideal gas. Okay, so the equation involved may be different from one to the other, but the concept is exactly the same. Try to evaluate what would be the deviation if we are moving from PV is RT from the ideal gas. If we are moving from this MI in the mixture is XI, MI pure, then what would be the corresponding real stuff? Okay.
Okay.
Moving to this next slide. So here is still this excess property for the liquid. And the next one is the mixing process, as we just discussed. So I have the property of the mixture, and that is the property of the each liquid component, pure liquid component. And we assume that we are going to connect that by the molar fraction over there. So now we have this n e m, could it be r, this could it be n, capital N itself, I could have mi, right? Let's put it pure. I could have mi with the hat. I could have mi with this hat. So try to distinguish when you see those various symbols. I hope you understand what those symbols are. Okay. And here I have this as the conclusion. We should be able to understand why I could have this conclusion. But basically, when you try to look at the excess property with the mixing property or the mixing property of excess, I hope you realize that there's no guarantee that the three will be identical. For the excess property and the excess property of the mixing, as we just derived, they shall be always identical to each other. However, the mixing is not the case. Okay. So the mixing property change, we have to look at what quantity you are interested in, and there we shall be able to tell you whether the mixing property is exactly the excess property or is actually not. So for this slide, pay attention. Do not assume that we are able to replace the mixing property always by excess property. Otherwise, there's no need to introduce the mixing property calculation as a separate topic. Okay.
That makes sense.
So moving forward, here I will on this next slide, I was trying to take a look at this partial molar property because we are going to use that in a minute. So we were talking about the partial molar property in the past when we were looking at the chemical potential definition. So here is the official introduction to this partial molar property. When I have this, you could understand this is a total of a mixture. On property N. In order to remind ourselves, so this is why we try to put this lowercase n over there, and n could be the sixth property of for energy, volume, and entropy. So over there, yeah, if we try to look at the fourth derivative with respect to temperature, with respect to pressure, and the summation to loop over all the components, then over here we define this as a partial molar property, and we have emphasized that I shall carry out the definition at this fixed temperature and pressure. So if you are going to have other confinement, then you cannot call this as a partial molar property. So the partial molar property has to be calculated at fixed temperature and pressure. So that is purely the definition of the partial molar property. And I want to also bring up this quite interesting note. This is a note you need to pay attention to. So you can see that we often manipulate moving from the number of moles to the molar fractions. Okay, so mathematically, it's quite common for us to think about the partial derivative of dmi, and then we try to somehow convert that into dxi. And we somehow develop the idea that they should be interchangeable. But here I want to bring up the note that when you try to define the partial molar property, we have to follow the physical meaning of this partial molar property. And over there, we cannot use the two equations. We cannot treat them as identical definition to partial molar property. So if we read the definition, it says in order to have the partial molar property, we need to have this fixed temperature, fixed pressure, and we have all those other components fixed. This is Nj. We are only changing the I component. And we try to measure the thermodynamic property, which is the six quantities we've talked about. This is U, A, H, G, volume, and entropy. We try to measure the change due to the addition of one more of component I to this infinite large system. So it's interesting that we in the lab, we try to have the measurement not on one molar based solution, but we try to assume that I'm going to have the infinite large system. Say for the other components, I have quite a large number of moles, tens, hundreds of moles. So the system is infinitely large. And then I try to add one more of that component I. And then after that, I want to measure the change due to this addition of one more of component I. And because of this partial molar property definition and how it's measured in the lab, so this is why we need to stick with this equation. We need to stick with this equation. Try to not use this one to define the partial molar property. So now if you look back on the previous slides, we never use the second equation to start any discussion on partial molar property. It's always a dm over dmi. Okay, it's always this equation for the partial molar property, and that's the starting equation or starting definition. Okay, so that is just one note, just in case you get confused on the two equations. So mathematically, they are very helpful to each other, and we always try to convert one into the other. But for the exact partial molar property definition, we'd better pick up the first one.
Dr. Hong?
Yep.
Can you explain the difference between mi bar equal mi? If for a pure substance, I understand they're the same, but how can a pure substance, the I indicates that there are different species, right?
Yeah, you're right. So
how can a
this is a little bit weird, but it's making sense that we always start the discussion from the mixture, right? So in the mixture, we have to have this I to distinguish one to the other. Then when you are moving to the pure substance, you automatically actually get rid of this I because you have only one component.
Yes. So M is just one component, right?
Uh-huh. So this is more like, now you're going to have this one. So this is the general symbol for the mixture.
Okay.
And then when you have the pure component, then you get rid of the head. It's no longer partial, right? And then you have one component, you get rid of this I subscript.
So on top, when you listed all the M's, what's the difference between Mi pure and M?
Well, if I have this M, I have to tell you this is the pure component. I have to explain to you so that you know this is the pure substance property. Otherwise, you may take this also as the property of the mixture. For example, if if I just write down volume V, you cannot tell whether this is the volume
You
of the
cut out.
mixture or the volume of the pure component. But if
Yes.
I write down this VI pure, you cannot have any confusion, right?
So that's saying that there is only one component and it is pure.
That's right.
That's
So
what that's saying.
yes, with the second
Okay.
symbol, I could just write down the symbol and you shall understand the meaning. But for the first one, I have to
Thank you.
explain, right? I have to explain that this
Yeah.
is for the volume of the mixture, or this is a volume for the pure substance. So it's a good question that this item 3 is not a useful equation. I'm just trying to explain that sometimes when you see those various symbols, you better ask yourself whether this is for the pure substance or that is for the mixture.
Thank you.
Right? Yeah.
Yeah, thank you.
Then here we are coming back to the UU business. For the partial molar property, for the fugacity, for the chemical potential, for the excess, for the residual, once we have defined that quantity of interest, we're always interested in expressing this as a function of TPX or TVX. So any property we've defined so far in thermal, we are always trying to express those properties as a function of PVT and composition. So those would be the choices we have. And we try to express the whole universe using TPVX. So that's another reminder that moving forward, we may manipulate, try to express those properties as a function of PVTX. Okay. So on this slide 11, it's more to explain, not to define any new quantity or any new equation. Yeah, on this slide 11. Moving forward, we do have a very important equation, which is the first one. So to simply explain, when we have pure component, and we are going to have this, let's use the volume. Use the volume for the example. So we have V1, we have V2, okay? Or V1 pure, V2 pure. And then we start to mix it. We're going to move from the pure to the mixture. Let's call this as V total, or as I have over here, let's call this as NV. So this is simply to remind myself that I'm going to have a mixture, and that volume of the mixture will be expressed by this symbol. So if I'm going to have for the pure component of 1 and 2, I'm going to add the number of mole N1, number of mole N2. And now in order to calculate this V total, we cannot directly use the pure volume for 2 components, but I have to use N1 V1 partial plus N2 V2 partial. And I cannot use V total is not N1 V1 pure plus N2 V2 pure.
Because
Okay.
the volume changes when we mix.
Yeah,
things.
that is the daily life experience, right? When you have water and ethanol, when you try to mix them, the total volume will be smaller than the simple summation of the volumes.
Okay.
So moving forward for any mixture, so in order to calculate the mixture, I have to understand this partial molar property. And that is the direct summation in order to receive the property of the mixture. Okay. So this is the most important equation so far in this lecture. And moving forward, it's also very important for the following chapters as well. So whenever you think about the mixture, you need to look for this partial molar property. And once you have that, that's a direct summation of those components, but not. So if I want to make it clear, this is pure. So you can see that even for my own slides, I cannot make it 100% consistent. So this is really meaning the pure component property, but that's not going to help for the mixture property. Okay. So on this slide, you see that we mentioned about not mixing this partial derivative with respect to n or with respect to xi. That is purely for the partial molar property definition. When you are calculating mathematically, it's quite common that, for instance, on this first equation, if we divide on both sides by the total number of mole, then we are going to receive this equation. That's also a valid working equation for the mixing process. So again, you need to know the partial molar property, you need to know the molar fraction, and the summation will tell you the property of the mixture. So again, n is U, H, A, G, volume, or S, 1 over 6. All right. I've explained those various symbols. Somehow pay attention to those different symbols. Do not get confused over the variations. Our next slide is another revisit to the previous partial molar property, which is the partial molar Gibbs energy, and that should be the same as the chemical potential. If you recall the definition of the chemical potential, we can take any of the 4 energy equations and derive this partial derivative with respect to component I, and any of the 4 shall be qualified as the chemical potential definition, but only the last one would be the also the partial molar property. So I think I have another slide. Yes, this one. So now when you look at the chemical potential and partial molar property, so I have 4 chemical potential definitions, right? And I can always calculate the partial molar property. But you can see that for any of the partial molar property calculation, I always have to satisfy TP, other composition fixed. Now when you go back to this, the previous chemical potential definition, only the last one with the help of Gibbs energy should be qualified. So the chemical potential is the partial molar Gibbs energy, but not the partial molar molar property of the other 3 energy equations. Okay. So again, nothing special. It's just a revisit of some concept we've discussed earlier. So now we have this first equation. Here is the first and the very important first equation. Let's try to see what would be the use of this. Number 1 is we divide on both sides by the total number of mole. So we are going to have the molar fraction based equation together with the partial molar property. And again, you may feel somehow confused about this, but this is just again some other note. When we are talking about the pure component, then this is indeed the pure. Then the pure would be exactly the same as if you do want to write down this as a partial molar property of the pure, then this should be exactly the same. Or more generally, we just use the pure. Get rid of the I, get rid of the head, and just add a note. This is the pure component property. Okay. So if we try to simplify to a binary mixture, then this n would be x1 partial molar property of m, x2 partial molar property of m2. Okay. So here nothing special. It's just a simplification to a binary system. Move forward. Let's see what's going on. I'm going to skip this for you to read in the following 3 slides. So basically, we introduce here another important equation. Let's give 2 stars to this one.
All right, I can do that.
Yep, I know you could do that. So here is a now I need to have this M1. If I'm using the binary system as the example, I need to have the M1 partial, right? I need to have M2 partial so that I can understand what is my n of the mixture or n total to avoid the confusion. But we can also have the opposite. If I have n total, if I have n1 partial, how do I calculate n2 partial? Right. So here with this equation and the following proof, this is straightforward, which is m1 is m1 partial is n of the total. So let's try to add total to avoid the confusion. Minus x2. So you are looking at component 1, but you need to use the understanding of the other component, x2 times dn of the total over dx2. Okay. This is the partial. So you can see that we are connecting those partial molar property calculations. So this is why we are having the partial. And I don't have the other components, but this is because we try to look at a binary system. Otherwise, you may have to use the note saying that other than x1 and x2, all the remaining components shall be fixed. Say x3, x4, x5, there will be no change to the other 3 components, but we only manipulate x2 in order to understand x1. Okay. So this is the useful equation for the actual calculation, and we started with the first useful equation to derive the equation for the mixing process calculation. So now if we try to look at the answer for the binary system, so that is m1 partial is m total minus x2 dm over dx2, keeping temperature and pressure fixed. And similarly, if you calculate m2 partial, that is the total of the mixture minus x1, the partial with respect to x1, keeping temperature and pressure fixed. So this is the equation we are going to use again and again in this chapter for relevant calculations. And sometimes we manipulate this equation a little bit. And I hope that you quickly see that for the binary mixture, we are going to have x1 plus x2 shall be always 1. And then if you manipulate it, then dx1 is negative of dx2. Okay. Then you can see that I can replace x2 by 1 minus x1. I can replace dx2 by minus dx1, or I can replace both. So this is why sometimes if you look at this equation, here we try to replace this dx2 by negative dx1. So this is why we are having the change. All right. And like I mentioned, we can also write down this as n1 partial is n plus 1 minus x1 dm over dx1, keeping temperature pressure fixed. So if that is the case, then we try to change both. We try to replace x2 by 1 minus x1. We try to replace dx2 by negative dx1. Okay?
Sounds good.
Should be. All right, so move forward. iPad gets stuck. Okay. I'm going to skip the proof and leave this to you if you are interested in reading. Otherwise, as long as we are happy with the equation we just received, shall be no problem at all for the calculation. So here is another summary of the equations. Those are the important equations when we are looking at the actual calculations. Let's give it 3 star for the calculation. Okay. So I have a diagram for you guys to take a look at. So this is how we are going to design the measurement in the lab in order to figure out, I think I'm missing this head. It's too windy, losing the head. So this is to tell us that I shall be able to design the measurement of the volume in the lab, and then we can try to take the measurement for both partial molar volume at this measurement. Okay. Let's try to look at one example to understand how do we utilize the equation we just derived. So let's say we are going to have a need to prepare this liquid mixture, methanol and liquid water, and we need to prepare this as a 20% of weight. I have the temperature, I have the total volume over there, and I need to know how many volumes of methanol and water will be needed. So basically we need to prepare a mixture, and I need to know how many volumes of the pure components in order to prepare that much of the mixture. And we have the following information, knowing that at this same temperature, the partial molar volume of the 20% solution would be this much. V1 partial, V2 partial. Oh, I should mention on previous slide. So you can see that the problem statement emphasizes that the partial molar volume of this mixture. So we have to mention the exact liquid mixture in order to figure out the partial molar volume. This is because if, for example, if I'm changing from this condition, this is x2 prime, I'm having a different mixture, then you are going to change the slope. Well, that's a bad one. Let's pretend this is the one. So the bottom line is, if we are changing the composition, you will see that the calculated V1 prime is also changing, right? I'm running out of space for this V2 partial. Okay, so this is why in order to talk about the partial molar volume, you need to completely define what is the composition, what kind of liquid mixture you have over here. Okay, so we know the partial, we know the pure component, also know that at 20 degrees C, this is the pure specific volume of methanol and liquid water. So we need to calculate V1 total, need to calculate the V2 total for the pure component. We understand the V, we also have the V1 partial and the V2 partial. So in order to calculate that, first of all, we need to figure out if I'm having this V total, then this V total should be expressed as M1 V1 partial plus N2 V2 partial, right? So I have to use the partial molar volume in order to have this mixture. And over here, if I know the number of moles, then it should be straightforward. If I multiply this M1 by V1, which is the specific volume of component 1, then I can tell how many volumes I need to have for both components. So how do I figure out the number of moles? Then this is the question. Well, if we start with this 20% of weight, we know the molar mass of methanol and water, so we can calculate what's the corresponding molar fraction in the liquid phase, x1 and x2. And if that is the case, then I can calculate this specific volume of the mixture, right? So I can have x1 multiplied by V1 partial, x2, V2 partial, then I can have this mixture. But keep it in mind, this is the per mole based volume of the mixture. And I know that is the total volume I need to prepare. So their ratio should be how many moles of that liquid mixture I shall receive, which is basically N1 and N2. Right? So
what's
if
the difference between V total and just V again?
Well, this is the reason why I explained in the previous part. When you read V, you have to put it into the context to understand whether this is a total volume or this is a volume for a pure component. So here, this is the total.
Okay. Okay.
Yeah, but you need to also pay attention that is the total volume with the per mole based, or this is the specific total volume.
Yes.
So now if I know the actual total volume, which is which is a problem statement that says I have 3 10 to minus 3 cubic meter, then I need to run the unit conversion, and I divide this specific volume. I can figure out what is the number of mole for the mixture. All right.
Seems to me.
And this is M1, which is also M2. For both components, I shall have that many of mole in order to satisfy the requirement. So now I know the number of mole. I know the number of mole. I know the molar fraction. No, this is wrong. Because I need to multiply by this molar fraction. This is N1. And that is the specific volume for the pure one, V1 pure. This is M2, V2 pure. V1 and V2 pure, the two values are also provided as the specific volume. So if I know the number of mole, then I can calculate the total volume needed for the pure 1 and the pure 2. Okay. And of course, if you run a quick check, then when I have this much of methanol, when I have that much of water, in the end, I mix them, I'm actually having this volume change. It's no longer their absolute total volume, but the total volume will shrink a little bit. So that is the calculation we need to perform for this specific example. The bottom line is we need to realize that M is x1 and 1 partial plus x2 and 2 partial, or total number of mole of M is M1 and 1 partial plus M2 and 2 partial. Okay, use one of them to finish the calculation. Let's have another example over here. It says at 100 degrees C, that much of pressure. By the way, for this part of calculation, it's relatively a peaceful calculation because we no longer need to worry about the temperature and pressure change, simply because this partial molar property, when we define it, we have to require that we are going to fix the temperature and pressure. So we no longer worry about the temperature change or the pressure change, and what would be the effect on the calculation. So that is the convenient part. Anyway, let's move on. So the volume here is the total volume. So again, you need to read and understand the equation with the help of the statement. The total volume of a binary mixture can be described as the equation below. A, B, C are constants, and we need to derive the expression of the partial molar volume and discuss the partial molar volume of the component 1 at dilute. What does that mean by dilute?
So small that it's non-negligible is the word.
Yes. Any math equation you can think of?
Oh, math. You want smaller than. Yeah, Henry's law is good.
Very good.
That
Or if I write down, this is partial molar volume, so this is V1, that is the partial molar volume of component 1, right? So we try to understand when Y1 goes to 0. So that is something we are going to discuss in the end.
Okay.
So that is the dilute when you try to push Y1 goes to 0. Okay. So we have the total, and we need to look at the partial. We need to have the V1, we need to have the V2, right?
Right.
So then we only have one equation so far, which is V total, or V. I hope you don't confuse. This is just V total. So here we are using Y1, Y2, then this is Y1. No. This is the first equation we have, right? The second equation, or the set of equation we have, is V1 partial is what? Is V minus the other component, Y2 dV over dy2. V2 partial is V total minus the other component, Y1 dV over dy1. Of course, this is at same temperature and pressure. So this is the other set of the equation. And the way we are going to use and calculate this problem. All right. So now, if this is the case, then we can start the calculation. For example, here in the solution, we try to utilize this one, which is a small modification of the one we have. So here we are changing, we are replacing Y2 by 1 minus Y1. We are also replacing this dy2. dy2 is negative dy1. Then you are going to have this equation. V1 partial is the total volume plus 1 minus Y2. This is dy1. Okay. So now we have this expression for volume. We have this expressed by Y1, Y2. It's always a good idea to add one more step, which I don't have on this slide. It's always a good idea to change this by A Y1, B 1 minus Y1, C Y1, 1 minus Y1. Okay. Otherwise, you may feel a little bit confused when you are going to have, you may feel a little bit confused by the two minus sign in front of the next step. So now you have this volume as a function of P of temperature, pressure, and Y1. ABC shall be constants. So now if you take the partial derivative of dV over dy1 at fixed temperature and pressure, then this would be 0. You have 2a y1, which is over here. You have this, the second term will give you this term or that term, and then you are going to have the two other terms corresponding to this one. Okay, so here I have also to have this modified. So my bottom line is that when you have multiple components, it's always a good idea mathematically to write the whole equation as a function of only one component, especially for the binary system. All right.
That makes complete perfect sense.
Yeah. So if this is the case, then we try to use this equation. Now I have this partial derivative. I have y1 known to us. We have the expression for volume. Then just reorganize those terms, and you should have the answer over here. Very similarly, you are going to calculate, for example, V2 partial. I don't think that is required. Yeah, I think the problem statement asks us to only calculate component 1. Fair enough. So now if we try to look at this partial molar volume at dilute, like we mentioned, in order to calculate the dilute, we just need to push this y1 goes to 0. Okay. So here we have this expression for the v1 partial. Then we just need to push this v1 to 0 to see what's going on. So if y1 goes to 0, this is 0, this is 0, and y2 will be 1 because y2 is 1 minus y1. When y1 goes 0, this goes 1. Okay. So then this is 1, then we have this expression. And we have a special symbol for this. So we have this. So you can see that we push this to the dilute. We are going to have this infinity, this maximum value for V1 partial. Keep in mind the V1 partial is depending on the composition. It may vary when you change the composition. So that is the maximum possible partial molar volume for component 1. It's a little bit confusing. I have a diagram to show you in a minute. So this is something of interest to us. And sometimes we also push y1 to 1. Then this will be the pure component of 1, pure 1, right? So over here, if we try to push y1 goes 1, and y2 is 0, then we have this expression. And that itself is a pure volume for component 1. So you can see that they are always connected, right? This pure molar volume, partial molar volume, total volume of the mixture, and the volume change from the pure volume to the total volume of the mixture. We should be able to calculate all of them. And the tool we have is that two equations. Okay. So again, I have this extra symbol expressed over here. When we try to have this molar fraction going to 0, then we have this so-called partial molar property at dilute, which is the maximum partial molar property we could have. And when we try to push the molar fraction to 1, then this is the, if I make it more clearly, then this shall be the molar property of the pure component I. Okay. So again, we've discussed that we need to pay attention to the symbol and understand what the symbol is referring to. Here is a diagram I have for you. So that's a very nice diagram, mathematically very nice. So this is the curve we have for the total volume. Okay, for the mixture. And I express this as a function of the component 2, meaning for this special condition, I have x2 at I have X2 at dilute, right? There's almost no no component 2, it's purely a component 1. So this is why this is a pure component. See the pure for the component 1 when X2 goes 0. Similarly, when X2 goes 1, over here, that is the pure component for X1, and then for component 2 over here. And then we also have the very nice stuff. So when X2 goes 0, then you try to take the slope. And that is the corresponding V2 partial molar volume at dilute, which is the maximum one we are going to have. Similarly, when you have this X2 goes 1 or X2 goes 1, X1 goes 0, then this is the corresponding maximum partial molar volume for component 1. Otherwise, if you are moving along the curve, then this would be the corresponding values. So you can see that this is a maximum partial molar volume you could have.
I like it.
So when would we need like V2 pure versus V partial molar to infinity? Like it's assuming that there is still a little bit of the other component versus a pure component. Is that the difference?
That's a good question. So the real stuff is to us, to a human being, this is the real stuff. Right?
Okay, so V2 infinity is fake stuff?
It's not a fake stuff. It's a mathematically or thermodynamically relevant stuff.
Okay.
So V1 partial, V2 partial, or V1 partial at infinity, V2 partial at infinity. Those are interesting stuff and relevant stuff to talk about the change upon mixing. It's a little bit weird to even to understand the language over there, but I hope that you somehow appreciate the discussion of those partial molar volume, because otherwise we cannot go directly from the pure to the mixture. No, there's no path there. We have to utilize the partial molar volume, and we calculate the total volume needed. And unfortunately, the partial molar volume is changing upon the composition.
Yes.
So
that makes sense.
V1 partial, V2 partial, they are not fixed.
They depend on X1 and X2, yeah.
Yeah, that's right. So this is why we are looking at, okay, what is the maximum possible value for this V1 partial, V2 partial? So this is the reason why we define
which is the V infinities.
Uh-huh.
Okay.
It's a good one. It's a good question. All right, so let's take a look at the last example. Is this the last one? Yes, I think so. Almost running out of time. Give me 2 more minutes. All right. So the problem is very similar to the previous one. We know the total enthalpy is depending on X1 and X2, and we try to calculate the partial molar enthalpy of 1 and 2, and we need to understand the pure enthalpy for 1 and 2, and we need to also understand the partial molar enthalpy at dilute. So the plan is still this one, right? So H1 is H minus X2 dH over dx2. Or if you rewrite this, it's H plus 1 minus x1 dH over dx1. And we have the equation entropy as a function of x1 and x2. So the very first step is I need to replace this x2 by 1 minus x1, so that I'm going to have the equation purely expressed as x1. And then I would use this equation to calculate for h1 of the partial, and very similarly I calculate the second component of h2. And now if I know this very general expression of partial molar entropy of component 1, it must be a function of x1, then I can take the limit. If I have x1 goes to 1, this will be the answer of the second part. If I have this x1 goes to 0, this is the quantity at dilute. Okay?
That makes sense.
So that's all I have, and I leave you guys to read the solution and figure out what is going on. It's nothing special, but you know, we are simply utilizing this equation. So the whole lecture is almost entirely based on this equation. Okay. That's all I have for you guys, and I don't think we will have a lecture on next Tuesday, so I see you next Thursday in the morning about the exam 3.
Dr. Paul, can you go to slide 25?
25, yes.
Yes, right there.
Uh-huh.
So for the second one, the second equation you've written, mi pure equals limit as yi approaches 1 of mi. So if we could that also be written as, if we had if we only had two components and one of them was going to 1, could it also be equal to the m partial molar infinity of 2?
That's a good question, but the answer is no.
Why? Because isn't it the same thing as the second component going to 0 if the first component goes to 1?
Well, I'm going to tell you why. Because for example, if you look at the expression, they are different. So you are right that if x2 goes 0, right, we are going to have this h2, which is h2 infinity of the partial. At the same condition, you have to use the expression of h1. No. Same as goes 0, then this is h1.
Okay.
So does that make sense?
No.
Oh,
I'll just,
you see that we for each component we have to use its own expression.
okay.
So we are using the same condition, x2 goes 0, and then for that condition, for h2, it's the partial molar at dilute. For component 1, that is a pure component of 1.
Okay.
Well, let me give you one other. Yes, go ahead.
On slide 25, those are, so then it's supposed to be two different, the equations, the first one describes component 1 and the second one describes component 2?
No, they're always talking about the same
But the same
component.
component. That's what I
Yeah.
was, okay, that's what I'm confused about, because you changed the component below. You changed it from H1 to H2.
Well, but they are two different conditions.
Okay.
The
Okay.
first one, so for any condition, you're going to have two changes. Let's say y1 goes 0. Then essentially you're going to have the pure component 2, right?
Yes.
And then we are going to have this h1 partial is h2 partial is h2.
Yes, because y2 is going to 1.
Yes, but at the same time for this h1, we almost have no h1 left. So this is why now we are
It's
changing this h1 as
H1 infinity.
h1 partial infinity. Yes.
Okay, that makes sense. That makes sense.
So again, if I have h1 goes to 1, then I will also have this two condition. Now I'm going to have the pure component of 1
H1 equals,
is
yeah.
h1 pure. Then h2 partial, I'm almost having no h2. That will make it to h2 partial infinity.
That makes sense. So it's just, so we're assuming that the final volume is mostly of one, and that the of 2 is almost 0, but not really 0 because it's so dilute. There is still some left. Okay.
Or one final evidence. Now, if you look at this one, you can see that at this condition, we are going to have this as a V1.
Yes.
Right? I'm going to have that as the V1 partial. So
Infinity.
they are indeed very different from each other.
Okay, that makes sense.
Uh-huh.
It explains the graph.
Yeah.
Thank you.
Mhm.